So here we want to talk about what it means when we say that two rings are isomorphic. So a ring R is isomorphic to another ring S if there exists a function between them so that the following axioms are satisfied. The first thing we want is that F is injective. The second thing we want is that F is surjective. And the last thing we need for this map F to be an isomorphism is for F of A plus B to equal F of A plus F of B, and F of A times B is equal to F of A times F of B for all A in the ring. So a couple things to note here. This last property is telling us that the addition in the first ring R is going to be identical to the addition that's in the ring S. Similarly, the multiplication in R is going to be preserved in this map and is going to be the same as multiplication in S. Now, a couple of notes about injective and surjective maps. Just as a refresher, we know that F is injective if when the image of R and R prime and S are equivalent, that implies that R is equal to R prime in the ring R. We know that a map is surjective if for each S in the ring S there is some R with F of R equal to S. So let's change there is some to there exists some R, so F of R equals S. So this says if we take any element in the ring S, there's some element in R that maps to S. Okay, so this is what it means for a ring R to be isomorphic to a ring S. We have that addition and multiplication is preserved in the mapping. We have the F is injective, and we have the F is surjective. So if all these three criteria are satisfied, we call the ring map an isomorphism. Okay, so let's look at an example. Here we have the set K, which is the set of 2 by 2 matrices of the given form where A and B are real numbers. And K is a field here. And so what we're doing is we're mapping K to the complex numbers, and the mapping is defined by this function definition right here. And we want to use this to show that F defines an isomorphism between this field K and the field of complex numbers. So we need to precisely go through and show that this field, this map F, satisfies the three criteria in our previous slide. So first, let's show that F is injective. So to do this, we're going to suppose that F of A, B, negative B, A is equal to F of R, S, negative S, R. So we've taken two matrices that are in our set K, and we're assuming that the image of these matrices are equal. And we want to show that that implies that the matrices themselves are equivalent. So by the definition of our map, we can actually write out what happens when we put these matrices into this function. So we get that here in this first statement, that's the same thing as A plus BI. And then here, this is equivalent to R plus SI. So by definition of what it means to be a complex number, two complex numbers are equivalent if they are. So what I'm trying to say is that A is equal to R and B is equal to S. So that means in K, we have that if we consider the matrix A, B, negative B, A, and we know that A is equal to R, we can substitute the R for A here. And if we know that B is equal to S, we can substitute the S in for B. And so, in fact, we've shown that if the images of two matrices in K are equivalent in in the complex numbers, then they're equivalent in our field K here. So this map is injective. Now we want to show that F is surjective. So what we want to do is we want to consider any element in the image of F. So consider a complex number, some complex number. So consider A plus BI and C. Then, because of our definition of our map, we have that F of A, B, negative B, A is equal to A plus BI. So what this tells us is that if we just pick any complex number, we can choose a matrix in K that maps to it. So that's precisely what it means for F to be surjective. So let me make sure the phrasing is written down correctly based on what I just said. So F is surjective Now the last thing we want to show is that F of A plus B is equal to F of A plus F of B. And then we want to show a similar property for multiplication of F of A times F of B. So let's just write out what we get. So if we take F of A plus B, so we're considering two matrices that are arbitrary in K. So I'll label the entries with A's, B's, C's, and D's. And so what is this going to be? Well, first thing, let's add the two matrices together before we put them through our function F. So this is going to be F of A plus C, B plus D, negative B minus D, and A plus C. So this is going to be A plus C plus B plus DI when we use the definition of our function F. And notice that we can rewrite this as A plus C plus BI plus DI. And then we can regroup and write A plus BI plus C plus DI. And this is precisely F of A, B, negative BA. And C plus DI is precisely the image of C, the matrix defined by the entry CD, negative D, C. So we've shown that the first part of the third criteria is satisfied, namely that the addition that we do in our field K, that's the same thing as the addition that we have in the complex numbers. So part 3 continued. The last thing we want to show is that F of A times B is equal to F of A times F of B. So once again, we'll start with two arbitrary matrices in our field K, and we will multiply them together. So when we do that, we're going to get the following matrix: AC minus BD, AD plus BC, negative AD minus BC, AC minus BD. And now, when we apply the function rule for f, we get that this is equivalent to AC minus BD plus AD plus BC times I. And then if we distribute, we get the following. And now we're going to regroup to get A plus BI, to get AC minus, let's see, what do I want to do here? I want to end up with F of this matrix times F of this matrix. So I want to somehow end up with A plus BI times C plus DI. Oh, so conveniently, that's exactly what we have. It's just an unfactored form. So A plus BI, C plus DI. Okay, so this is what we want. So now A plus BI is precisely AB, F, and then this is precisely F of this matrix. Okay, so what we've shown here is that if we are starting with this field K and we're mapping it to the complex numbers, the map that we define gives an isomorphism between K and the complex numbers. So this means that we can think of our field K as structurally equivalent to the complex numbers by showing that it's injective, surjective, and then showing that the multiplication of elements in K behaves the same way as multiplication of elements in the complex numbers, and the addition of elements in the complex numbers behaves the same way as the addition of elements in our field K.